This clip introduces a simple and intuitive derivation of the control law governing a PI controller. To do so, we model both the actual, open-loop behavior of the system to be controlled, as well as the desired, closed-loop behavior of system and controller combined. The control law derives from the requirement that actual and desired behavior must coincide. So, let's start with the equation that models the actual, open-loop behavior of the system to be controlled. A PI controller assumes this to be an integrator with X capturing the system's output behavior and U the input that is applied. The input can be further decomposed in a command imposed by the controller and a load component, which the controller will need to compensate for. Our second equation models the desired closed-loop behavior. The PI controller shapes this to be a simple first-order response. The control law derives from requiring the actual and desired behavior to equal each other. Through substitution and rearranging the result, we get the fundamental law governing the PI controller. Let's have a closer look at the components in the command applied by the controller. The yellow component is proportional to the error between the desired output and the actual output. This is the controller's proportional action, which is designed to get the system on track. The red component compensates for any external load. This component corresponds to the controller's integral action, which is designed to keep the system on track. The hat on top of this variable indicates that it represents a best effort estimate of the load. The details on how this estimate is derived will be explained later. It is straightforward to draw these equations as a block diagram. There is the proportional action that acts on the control error to get the system on track. There is the integral action that adds an estimate for the external load. Combined together, they produce the actuator's command value. Next, we dig into the details on how the load is estimated. First, we derive the load estimator out of first principles, detailing the specific choices a PI controller makes in its implementation. We'll show how these choices amount to an integral action. Later on, we'll discuss other choices for the estimator design, each of them yielding different variations on the standard PI controller design. Again, the starting point is the equation that models the open-loop behavior, an integrator driven by the controller's command and burdened by a load. Rearranging this equation calculates the load as a function of command and system rate of change. This raw load estimate is filtered to suppress components resulting from differences between the real system behavior and the ideal model assumed by the controller. A PI controller selects this filter to be a simple first-order low-pass one. If the time constant of this filter is larger than the time constant of the controller's transient response, which is shaped by its proportional action, the contribution of the rate of system change will be suppressed by the filter, and it can be ignored in the load estimation. Remember, though, the price to pay for this simplification is making the load estimator slower than the response time of the closed-loop system. What does this mean for the overall control law? The overall control law sums the proportional action to handle transient behavior and the load estimate to handle steady-state behavior. Substituting result derived above for the load estimate yields the complete equation describing the control law of a PI controller. Let's have a look at the corresponding block diagram. As discussed before, the major parts of the block diagram are the proportional action and the load estimate coming together to produce the command value. A filtered version of the command value is fed back to produce the load estimate. A standard PI controller implements this as a first-order low-pass filter. Anyone familiar with a PI controller will recognize that the block diagram does not correspond to a classical representation. As its name suggests, a PI controller sums a component that is proportional to the control error and a component that is proportional to the integral of the control error. In what follows, we will show that the block diagram on screen is equivalent to the classical representation. To do so, we return to the equations. In our formulation so far, a PI controller adds a proportional term and a filtered version of the command as a load estimate. Let's see how we arrive at the classical representation from here. We start by moving the second right-hand term to the left-hand side. Since both terms contain the command value, they can be grouped together. Next, we add the terms between the brackets, and we bring the resulting coefficient to the right-hand side, which is an operation that has it inverted. The inverted coefficient can be expanded in two terms, one equal to unity and one that is inversely proportional to the Laplace variable s. expanding the equation, and with 1 over s being the Laplace domain representation of an integral, we see the command value to equal the sum of a term proportional to the control error and a term integrating the control error. This corresponds to the classical representation of a PI controller, which is what we set out to prove. The classical representation certainly has its merits, especially when it comes to understanding how some physical systems naturally implement a PI controller. We'll see some examples as we study electrical circuits later on. However, from a control design perspective, the initial formulation is more useful as it comes to modifying and expanding the controller and its properties.